Hi. In this lecture video, we will look at one of the most famous quantum algorithms called Shor's algorithm. So, given two prime numbers p and q, it's fairly an easy task to multiply them together and find the outcome. But it's generally harder to perform the inverse process, that is, given a large integer n, given a large integer n, which is equal to p and times q for some prime numbers p and q. The problem is to find p and q. Find the prime factors p and q. Now this is not an easy task. If the integer is small, it might be fairly easy to solve this problem. But if n is a large integer, it gets harder and harder to find its prime factors. Now, the fundamental theorem of arithmetic says that any natural number greater than or equal to 2 is the product of prime numbers. And what's more is that this product is unique. Okay, so this is called the fundamental theorem of arithmetic. And in fact, given any integer, we can algorithmically decide whether that integer is a prime number or not. This is polynomial time solvable by classical computers. And there's also a known algorithm called Euclid's algorithm, which goes back to, obviously, Euclid. This is an efficient algorithm for determining the greatest common divisor of two given numbers a and b. Okay, so to know the GCD, the greatest common divisor of a and b, we use Euclid's algorithm. So this is essentially to determine if a and b are relatively prime, for instance. So we know that a and b are relatively prime if and only if the GCD of a and b is equal to 1, are relatively prime. So we can use Euclid's algorithm to determine the greatest common divisor of two given numbers. There is a nice recursive definition for finding the greatest common divisor of a and b. This is given in the lecture notes. I encourage you to look at the recursive definition of GCD. So we're looking at a special case here. So given a large integer n, we want to find its prime factors p and q. Okay. So, but why is this important? Well, because prime factorization of integers is frequently used in RSA cryptography. And the reason behind why cryptography systems use integer factorization is due to the fact that there is no known efficient classical algorithm known which solves the integer factorization problem, the prime number factorization, in polynomial time. So there is no known, let me write that down, there is no known polynomial time classical algorithm which solves the prime number factorization problem. So Shor's algorithm is actually a quantum algorithm which solves the integer factorization problem, or more specifically the prime number factorization problem in polynomial time. In fact, the best known classical algorithms that can solve this problem only can solve this problem in exponential time. Because let's consider the worst case scenario. So suppose that we are given a large integer. Suppose that we are given n, which is equal to p times q for two prime numbers p and q. So the problem is that we want to find its prime factors. So we want to find p and q. We want to find what p and q are. Okay, so we know from algorithmic analysis, that we measure the complexity of an algorithm in terms of the length of its input. Now, the size of n is measured in bits, right? We measure the size of n in terms of bits. And size of n is approximately, let's denote it by w, it's approximately log 2 to the base n. Right? So this is the size of the binary representation of n. So we have that big O n is equal to big O 2 to the log 2 base n, and that's in terms of the input size, that's 2 to the omega. So we solve the integer factorization problem in 2 to the omega, big O 2 to the omega, if the input size is measured with, is denoted by omega. And Shor's algorithm reduces the complexity of this problem to polynomial time. Now, before discussing how Shor's algorithms works, we need to look at some basic number theoretic notions, and let's review some basic subjects in number theory and roots of unity. Okay, so the problem of factorizing integers can be in fact reduced to the problem of finding the period of a function of a certain kind. Now, modular arithmetic and integer factorization are in fact related to each other in some way. And this was discovered by Leonhard Euler, the famous mathematician. So let's say that A is equivalent to x mod n if x is the remainder of A divided by n. Okay. Now, there's a really nice relationship between exponential functions and modular arithmetic discovered by Leonhard Euler. Consider the function f of k equals 3 to the k. Let's take a look at the behavior of this exponential function. So we know that 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, 3 to the 4 is 81, 3 to the 5 is equal to 243, 3 to the 6 is equal to 729, 3 to the 7 is 2187, 3 to the 8 is 6561. Okay, but then what happens if we apply modulo 10 to this function? Okay, so now we consider the function 3 to the k mod n. Okay, now 3 to the 1 mod n is equal to 3, and 3 to the 2 mod n is equal to 9, 3 to the 3 mod n is equal to 7, 3 to the 4 mod n mod 10 is equal to 1, 3 to the 5 mod 10 is equal to 3, and then this goes on. Then the next number is 9, 7, 1, and so on. So this is a repeating sequence. It goes like 3, 9, 7, 1, 3, 9, 7, 1. Right? It's a repeating sequence. So the last element of the cycle is always 1. It always ends with 1. Apparently, for the given function, for a function f a n x equals x to a to the x mod n, so as long as a and n are relatively prime, then it turns out that we always have this cyclic property. Okay, now interestingly, integer factorization problem can be reduced to the problem of finding the period of such functions. And quite expectedly, period finding of a function is the hard part for classical computation. But we will solve this problem, the period finding problem, efficiently using a quantum algorithm, using Shor's algorithm. Okay, so Shor's algorithm is in fact is a hybrid algorithm which uses classical algorithms and quantum circuits. And the quantum algorithms is used to solve the period finding, for finding the period of a function, and for the rest we use classical algorithms. So let me discuss how we actually solve the integer factorization, how we find the prime factors of a given integer. I'm going to do this with an example by keeping n as small as possible, so that would be easy to observe how the algorithm works. So right now I'm going to show you how to classically solve the integer factorization problem. Okay, the classical approach. To the integer factorization. Okay, so let's note this. Note that integer factorization problem can be reduced to period finding. And by period, I mean the cycle lengths. Okay, so the period of this function, for instance, is r equals 4. Okay, the length of the period is 4. All right. So more formally, the least number r such that a to the r mod n equals 1 is called the period of f, a, and x. Okay, so the period of f3 and f310x is equal to 4. Okay, as we saw earlier here. So the algorithm for integer factorization can be written in the following manner. Okay, now suppose that we are given an integer n, which is equal to p times q for two prime numbers p and q. Now our goal is to find p and q. All right. So I'm going to write this in steps. In step 1, we start with picking any integer a less than n. So pick any integer a smaller than n and see if a and n are relatively prime. See if a and n are relatively prime. We do this by using the GCD function, and we basically see if GCD a n is equal to 1. If it's so, then we say that they're relatively prime. If they're not relatively prime, if the GCD of a and n is not equal to 1, then we found a common factor, right? And that must be a common factor of n. So that means we must have found one of p or q. In this case, we can output the factors and we're done basically. If we know one of p and q, then we can certainly know the others. Okay. So in this case, no need to process further. Just output p and q. okay? But if A and N are relatively prime, if GCD of A and N is equal to 1, then we continue with step 2. And step 2 is that we compute the period of the given function. Step 2, compute the period of FAN x, which is equal to a to the x mod n. Now this is the hard problem for classical computers, finding the period of this exponential function. It takes exponential time using classical algorithm. But we will solve this step using Shor's algorithm in polynomial time, okay? All right, but let's suppose that we have a classical algorithm and we compute the period of f. Let's call this period, r, okay? So next we see if r is even. If r is odd, then we go to step 1. Go back to step 1. Pick some other integer a less than n, satisfying the same property. So we're looking for a period which is even, actually. Okay, so, but if r is in fact even, then we see if a to the r divided by 2 plus 1 is equivalent to 0 mod n. Okay. If this is true, then we again go back to step 1. But if it's not true, if it's not equivalent to 0 mod n, then we continue with step 3. All right, so what's step 3? Well, step 3 is basically we play with some algebraic expressions. Step 3. All right, so we know that at this stage a to the r is 1 mod n. But then this means a to the r minus 1 is equivalent to 0 mod n. So that means there must exist some k such that then there must be some integer k such that a to the r minus 1 is equal to k times n. Now we also know at this stage, we also assumed that r is an even number. Okay. Since r is an even number, then we have that a to the r over 2 minus 1 times a to the r over 2 plus 1 is equal to k times n, which is equal to k times p times q by definition of n. So then we solve step 4. We solve p and q as follows. So we let p be the GCD of a to the power r over 2 minus 1n, and we let q to be the GCD of a to the power r over 2 plus 1n. Okay, so why does this work? Well, here let's take a look at this equation star. In the equation star, we know that p must divide one of the factors on the left-hand side, right? And q must divide the other factor. But they cannot divide the same factor because otherwise the factor would be divisible by n. But neither factor is divisible by n because we assumed at step 2 that a to the power r over 2 plus 1 is not equivalent to 0 mod n at step 2, right here. Also assuming that r is the least number which satisfies the equality r to the power r is equivalent to 1 mod n. So then we know that r to the power r over 2 minus 1 is not equivalent to 0 mod n. Okay. And since p and q divide separate factors on the left-hand side of this equation star, we can assume that p divides one factor and q divides the other factor. Okay, so the order here doesn't matter in fact. But we know that if p divides one factor, then q must divide the other factor. Okay, so that's how the algorithm works using classical computer. And we solve this problem using classical computers in exponential time. The best known classical algorithm solves this problem in exponential time, unfortunately. And there is no known polynomial time algorithm that solves this problem. All right, so it's a difficult task for classical computers to solve the integer factorization problem. But on the other hand, for quantum computers, it's quite easy to find the period of a function. The hard part for classical computers is to find the period of a function, finding the period of an exponential function. But we will transform the period finding function to another type of problem, and instead we will solve that problem using Shor's algorithm, and indirectly we will solve the period finding problem. All right, so next is to look at the mechanics behind Shor's algorithm. So integer factorization problem is relied on period finding, but the period finding problem is relied on phase estimation problem, which is relied on quantum Fourier transform. quantum Fourier transform. But before we go into the details about the quantum Fourier transform, we will now review some complex analysis, very basic complex analysis, a subject called roots of unity. So we will discuss that in the next video.